Perfect. Okay, so this will be the hands-on demo. We're going to be using a package called OpenMapFlow, which we have been working quite a lot on over the past few months. My name is Ivan, and I'm a machine learning engineer at NASA Harvest. So basically, this means that if you have a computer, you can take it out because you'll have the opportunity to actually work through some of this demo. So this is the last part. We'll go about till 5:30. Maybe we'll end a little bit earlier if people are efficient. We'll see how this goes. So over the next 90 minutes or so, I'll be covering these 5 things. First, I'm just going to give a brief recap on why I work with Earth observation data. We've been talking about this for a bit, but there's kind of 3 key points that I want to mention. I'll give an overview of OpenMapFlow, which is the package that we'll be using. And then we'll train a model all together, and that's going to be the hands-on portion. And at the end of that hands-on portion, basically everybody's going to have an opportunity to post their model results to GitHub. And I'm going to pick the best model, and we're going to use that one to make a large map. So there's some incentive to actually train a good model there. And lastly, we'll talk about future work that NASA Harvest is doing and future work for this particular package. So why work with Earth observation data? Kind of 3 key reasons that we boiled it down to. First, ability to contribute to urgent societal challenges. We've talked a lot about food security and this whole kind of process of taking satellite imagery and extracting insights related to what's growing where and what sort of yield you might have. But this is just one of the many potential urgent societal challenges that can be addressed using remote sensing data. Over here, I have a picture of the Allen Coral Reef Atlas. There's quite a lot of work mapping the coral reefs that's using remote sensing data. Open Buildings is a project that Google has put out with. It's important to know where buildings are for many humanitarian efforts. And in general, these are just some of the ones that, some examples that are using remote sensing data, and in many cases using machine learning and deep learning to actually generate these insights. Another reason to work with Earth observation data is because there's so much data becoming available now. Catherine and Hannah have both touched on this. I'm just going to talk briefly about the distinctions between some of the data that's available. Google Earth Engine, that's a place where you can get, there's literally petabytes of data available, so it's like thousands of terabytes. And there's data from all these different satellites, but part of the issue there is that you actually have to figure out which satellites to use. You have to figure out how are you going to associate your labels to the data. So that's might require some effort. Radiant ML Hub is kind of a step down in the level of effort. The data set's already combined with labels. All the Earth observation data is accumulated for you, but you still need to write your training model code and that sort of stuff. Crop Harvest is a data set that we've developed, and the advantage with that data set is that, first of all, it's pip installable, so it's very easy to access. And we've gone a step further where we make all the data available, we make the labels available, it's all combined together in machine learning ready format. And then we actually provide all the code for you to train benchmark models. So really lowering the learning curve there. The last reason to work with Earth observation data is that there's really a lot of space for novel research. So Hannah talked about this a bit, and I'll just recap because I think this is a really important point. When you're working with images, which is the case with pretty much all computer vision projects, you're training on a massive data set. ImageNet, for example, has millions and millions of images, and these images are all independent. And so once you've trained a model on those images, then you can do inference on another set of images, and you do inference on images that are also independent. And you hope that your distribution kind of matches, because if the training distribution and the test distribution is similar, then you'll probably get fairly good results. With remote sensing and with Earth observation data, this is not the case. You're training on what's likely independent Earth observation data points from around the world or around a particular region, but then you're doing inference on dense pixels on a dense region. And so the points are not exactly independent. And so using the same paradigm as computer vision is not going to get you all the way to your goal. And so we've called this dense inference, basically inference over a dense region of data. And the key point is that model inputs and outputs are not independent. And so there's a lot of kind of potential research novel research really that might come out from even just working on dense inference, such as domain shift and unsupervised learning. But this is also just one potential area of novel research. There's a lot of stuff that is relevant when you start diving deep into the remote sensing data and applying machine learning there. For example, few and zero shot learning, semi and self-supervised learning, super resolution, so taking basically images that are low resolution and making them much higher resolution, improved spatial encoding. So Hannah mentioned that a lot of models actually benefit from just the temporal dimension only. So actually using the entire image is an active area of research. And then foundation models. There's so much data out there that there's really space for large foundation models to be built now. So these are the three reasons. You have the ability to contribute to urgent societal challenges. There's so much data available now, and there's space for all these kind of novel research areas. So we've talked a bit about why I worked with Earth observation data. Now we'll go over this package. And first I'll just mention why this package, why we even made it. Basically, it's because dense inference is not easy. We were spending a lot of money setting up virtual machines and trying to make these large maps for entire countries in many cases. And so this is perhaps the reason that it wasn't easy is the reason that it hasn't really been explored as far. And so OpenMapFlow, this package that we'll be demoing today, is basically meant to make dense inference easy. And it does that by having these three components. It provides a data processing pipeline, machine learning model training, and then the ability to do rapid map creation, in other words, dense inference. So we'll flip this bar sideways and just talk in a little bit more detail about the components of OpenMapFlow. The first part is the data processing pipeline. The data processing pipeline is basically all the code that you need so that you can just come with a simple CSV or maybe like some sort of data in the table. And all that the data needs to have is a column for a label like crop or not crop or maize or not maize, a latitude, longitude, and that's it. So just those three columns. If you have those in your CSV, then you can basically run the data processing pipeline on that code, and it'll get the Earth observation data for you from Earth Engine. It'll combine the labels to the Earth observation data. It'll store it on some sort of remote storage like Google Drive for you. And then you have machine learning ready features to play around with. And so once you have those machine learning ready features, you can do machine learning model training. And the real advantage, or kind of a secondary advantage after the dense inference of OpenMapFlow, is that you can actually use any sort of PyTorch model architecture with this. It's very open in terms of the types of machine learning models you can try. And that's not something that can be said about a lot of other services. For example, Google Earth Engine is really useful for making maps. But one of the issues is that it can be a pretty massive hassle to actually try and get a deep learning model into Google Earth Engine. They have random forest classifiers available, and those are great to use. But if you want to do novel research, you want to explore these kind of new models that are coming out, and it's not super easy to just take, a model that somebody has written in PyTorch and convert it into something that Earth Engine can use. So with OpenMapFlow, you can use any PyTorch model as long as you have the shapes correct. And then rapid map creation is the main advantage of the package. We basically provide code to deploy Google Cloud architecture, which does this kind of scalable inference super fast because everything is parallelized. So this is the entire architecture, and it's available on the Python package index. So basically, if you have a Python environment set up, you can run this pip install OpenMapFlow, and you'll get this first version of it, and you'll have these three things available. And so I'm just going to quickly show some examples that we've generated with OpenMapFlow to just show what it's able to do. So we fed in this image, and we trained a non-crop model. So a model that basically predicted for each pixel whether that pixel was crop or whether that pixel was non-crop. And so the output that we got is something like this. And you can see there's some kind of yellow sections over here, that's the non-crop sections, and some green sections over here, that's the crop. if we go back, you can see it, indeed, it looks like fields over here, and it looks like maybe a mountain beginning or just some greenery on the left-hand side. So that was a crop non-crop model, and that's actually one that we're going to be training today. We're basically going to make this thing together. We trained another model to classify whether each pixel is a building or not a building, and you can see there's kind of all these large industrial buildings over here, and so we'd hope that the model gets those. And indeed, it basically says that all these are yellow, and that means they're buildings. There's also some streaks over here, which are yellow, and if we go back, we can actually, maybe if you're sitting in the back, you can't see this, but there's actually some little tiny squares over here that look indeed like buildings. So it's like this model didn't do a bad job. And then we trained another model in OpenMapFlow to classify whether things are maize or not maize, so a specific crop type, because in many cases you want to go beyond the crop, non-crop sort of classification. And so we got something like this as the output. Okay, so once again, OpenMapFlow has these three components. We are not going to demo the data processing pipeline today, just because that'll take some more time. Instead, we're going to use example data that we've already processed. So that part is done for us. The machine learning model training, that's going to be what everybody who has a computer out will have the ability to do. And then rapid map creation, that's going to be me picking the best model, or the model I think is the best, and making a larger map using our architecture that was deployed with OpenMapFlow. Training a model, hands-on. Okay, so basically, this is the start of the interactive session. So what you can do is actually write in this link into any browser that you'd like. And hopefully the Wi-Fi speed will be fast enough for you to do this. I have Ethernet connected, so my internet speed is going to be great. For those on Zoom, you should be doing a good job too. So I'm going to go ahead and click on this link, and the first thing to do here is to actually fork the repository. So I'm going to start doing things live now. I'm going to open up GitHub, and that opens up the OpenMapFlow repository, and I'm going to click fork on this repository. And so the reason that I want to fork it is because that's basically going to make all the example data available to me. So I'm going to create a fork, and that's going to basically make a copy of this project in my GitHub account. And that's basically it. So now you can see at the top I have my username /OpenMapFlow. So that's where I want to be. And if I scroll down in this package, if I scroll down to the README section, I can see there's a tutorial section. And there's an open and call-out button. We're not going to press it yet. We'll just read out the prerequisites. Probably should have mentioned this before, but you need a GitHub account, basically, because all this code is going to be on GitHub. You also need a GitHub access token. And so we're actually going to get the GitHub access token right now. And then we're going to go into the Colab notebook. So for the GitHub access token, there's instructions that are available with this link over here. So I'm going to open this in a new tab. And you can look at what the instructions are here. And I'm going to walk through them live right now. So if I go back to the GitHub page, I know the instructions off by heart at this point. There's like 3 steps. Basically, you want to go click on your profile and scroll down to settings and open the settings in a new tab. Once you've opened settings in a new tab, you can scroll down into developer settings. And then there will be this personal access tokens bar. And once you've clicked on personal access tokens, then you can click generate new token. And it'll ask you for a password, for your GitHub password, which hopefully you know. And then you can call it something. I'll call mine CVPR. And I'm going to click repo. And I'm just going to pause here for a second so people have the chance to ask any questions. If you've missed something or if something is unclear, let me know. Looks like there's nothing on Zoom for now. Yep. Yes, yeah, exactly. Yeah, so yeah, I should have mentioned this. So repo scope is all you need, because basically the idea will be that we're going to use this fork because then you'll have the ability to make a pull request into the actual the real repository, and that pull request will actually contain the model which you'll train. And so once we merge somebody's pull requests in here, if we get that far, then that model will be deployed into our architecture. So you just need the repo scope over here. You can call it whatever you want, and I'm going to move on and generate a token. This is my token, and there's a little button over here to copy and paste it. Once you've copied it, it's going to disappear once you close this. So maybe you can save it somewhere, somewhere in a notepad or something like that. Or you can also just keep it copied. We're going to use it in just a second. All right, so if I go back to the OpenMapFlow repository page, now we can finally get to the tutorial. All the kind of administrative, not so fun work has been done. And we can click on this tutorial where it says open in Colab. So this is going to open Google Colab, and Google Colab is a nice tool for really for demos. It's a nice tool for a lot of things, but for demos especially nice because everybody's going to have the same environment. So we'll pip install some things, but if everybody's doing it locally, they have different Python versions, they have Windows machines, and it just becomes a whole ordeal. So Google Colab makes this whole ordeal a lot simpler. All right, so we'll scroll down, and there's actually an editable Google Doc for Q&A. So I'm going to open this in a new tab, and we're going to use this Google Doc as a kind of question and answers as the demo is going. And so if you got this far, maybe you can write your name just so I have a sense of how many people have made it. And I'll just delete things as we go along. It doesn't have to be super structured. I just want to kind of get an idea of if people made it. And it looks like there's okay, maybe David, maybe not in the title. That's a little bit that one's a little too bold. Yeah, you got to put it below. Anyway, that's good. So there's some people here, and basically, if you have questions, this is also relevant for people on Zoom. I'll try and check the Zoom chat, but I'm ultimately going to be paying more attention over here. So if there's something that you see that is very confusing, then you can write it there. All right, we'll scroll down and we'll start running this notebook. So how you can run this notebook is there's going to be a play button that appears when you hover on the cell, and you can run the play button, and it's going to say this notebook was not authored by Google. So warning, it was authored by me, somebody more trustworthy than Google. So you can click run anyway because it won't cause your computer harm. You have to believe me at least, then it won't. So this is where it asks for the GitHub token. So you can paste it in here if you copied it before. It asks for your GitHub email. So I'm going to type mine in. And the GitHub username. And so this is all needed because we're going to be making a pull request afterwards. And once you've got that, you can run the next cell. And it's just going to show you the GitHub clone URL that you'll be using. So basically, if you fork the repository, you don't have to change anything here. This is the default URL should be correct. But if you have some weird issue with your username, the GitHub clone URL may not be correct here. But basically, everyone's forked it here, so it should be fine. So this cell you can move on from, and you can run the next cell. And this is what's going to start doing a couple of things. First of all, it's going to clone the repository, your forked repository. And then it's going to install OpenMapFlow as a package. And then install some other fun packages, even a specific version of PyYAML, because Colab is not a fan of PyYAML version 6. So we have to be very specific. So you'll basically get these bars, and you might get some warnings that come up. The warnings are just going to be version mismatches that pip doesn't like, but for our purposes, they're fine to ignore. So once this is all done, you can actually start running the next cell. While this one is running, it's just going to wait until the previous cell is run, and then it'll run the following cell. So if everything is installed correctly, once this above cell is done, then the below cell is going to show you the command line interface for OpenMapFlow. And the command line interface is useful once you've done the tutorial and you're a little bit more comfortable with the tool. Me personally, for example, I'm mostly using command line versus notebooks. So this is what I have as an output. So I'm going to go into Google Doc and check if there's any questions, if people are fine. I'm going to delete everybody's names because we're past that part. But if you have had, if you got to this part and it's installed correctly, then you can maybe write, I don't know, installed or something, just so I have a sense of how many people have made it here and if I can keep going or not. I guess actually, yeah, this is still kind of the not so fun part, installing and cloning things. Now that we're done here, and once I see, maybe if I see 5 or 6 names, I'll keep going. We'll actually start playing around with the data, training a model, and then eventually deploying the model. 1, 2, 3, 4, 5. Okay, so I'm waiting for maybe one more person to install it, or maybe we just lost. I feel like there was like 7 or 8 people before. So let's see if some people catch up. And I'm going to close these other pages. I don't need them anymore. Still 5. All right, maybe that was harder than I expected. Oh, that's true. Okay, nice, David. David, good job. I changed the name from here. Perfect. All right, someone got this error. Let me see if you can maybe you can post it, and I can look at it. Okay, so I think this is yeah. So that's actually not an error. This is the version mismatch I was talking about. I have these errors over here. They make it all scary, but it's really just like pip versions that are not matched properly, but everything still works. So basically, if you have this output, you're fine. All right, great. We will keep going now. So we're going to start running the next cell. The next cell, we're actually going to pull in data from my Google Drive. It's a public folder, and we're using this package called data version control to get it. So in order to pull in data from my Google Drive, you have to log into your Google Drive. So you have to click on this link and select your Google account. Click on the 2 boxes to allow access to Google Drive. Click continue. You get another fun token, which you can copy and then paste it where the cursor is flashing. And so what this is doing now is that this code is pulling in data, features, actually machine learning ready features from my Google Drive folder, public Google Drive folder, into Google Colab over here. And we're using data version control because often with a lot of machine learning research, people kind of just have a data set and they work with it, they run experiments and they're happy. But when we're working on a real machine learning, kind of real world life machine learning project, we're actually often doing iterations on the data. We're adding more labels, we're removing labels that are bad. And so we need to version that. We need to basically track the changes to our data set, and this package allows us to do that. And so everyone's pulling in the latest version, and it might take a couple seconds. But basically, once it's done, you'll have data that's available, and I'll show you where it is. If we go on the sidebar, the file where it says files, and we open OpenMapFlow, which is the repository that we clone, we're working with the crop mask example, and there's a data folder over here. And so, believe it or not, but these folders, like the process labels, were actually empty before, but now they have data in them, and this data came from the Google Drive. So I'm going to hide this and run the next cell. And this next cell basically shows a report of the data sets that we have available. Also, actually, I should have asked at the beginning, is this big enough? Is this large enough for the people in the back? Can you actually see the text? No? Okay, maybe I'll make it one bigger. 75. Is that a little better? Okay, perfect. All right, so this is the data that we have available within this crop mask example project. We have a global data set, GeoWiki Land Cover 2017, and it has over 30,000 labels, so that's a lot. And then we have Togo 2019, which is a regional data set, and that one we have different subsets. We have training, testing, and validation, and there's a lot less. There's only a couple hundred in each of those subsets, and there's different amounts of crop in each different subset. So, but I see all these check marks. So basically that means that the data is consistent, that all the labels have Earth observation data paired with them. So I can keep going and we can start exploring the labels. So we have to import some other packages to basically start looking at the labels. The labels are just CSVs, and the main columns in the CSVs are the longitude and latitude columns that I talked about, and there's also a class probability column. So what we just did right now is we basically took Togo 2019 GeoWiki, concatenated them together right over here, and then we just showed the first couple of columns in these labels. And we have some other columns over here. One of the interesting ones maybe is num labelers. For a lot of these points, there were many labelers, and so when you see something like 0.136, basically this means that most people out of this group had labeled it as non-crop, but there was somebody who labeled it as crop. And so there's not perfect agreement for that particular point, but it's still useful, and most likely it's still non-crop. So that's what we have in the labels. Now we're going to plot these labels onto a world map to kind of get a sense of the distribution. So first we'll plot the world, and here is the world. And then we will take a look at what's inside the world. In this case, the world is another data frame, and it's a geodata frame. So it has these it has a geometry column, basically, where every row represents a particular polygon. And so this is basically like the same thing as pandas data frames, but they just have this additional column. So we're going to take our pandas data frame and convert it into a geodata frame by making a point for using every latitude and longitude by running this next cell. And once we have this geodata frame, then we can actually run the following cell and plot our labels onto the world. And so it'll look like this. And you can see, here's a legend, Togo and GeoWiki land cover 2017. You can see Togo right over here in Western Africa. Pretty small. GeoWiki is all around the world. So I'll take this opportunity to check if people have any other errors. In the chat, it looks like nothing has been added, or I just deleted everything, but nothing was added before I deleted anything. So we'll keep going. I guess actually, since this is a room, maybe people can give a thumbs up if they got to this point, if they're doing it on their computer. Okay, great. There's enough thumbs up. Okay, we'll just quickly open up the geodata frame columns just to have them handy. And then we're going to run the next cell. And this cell is going to just plot Togo for us. And it's going to actually plot Togo plot the points in Togo by subset. And so it's important to take a look at the distribution of the points, because let's say you're making a map for Togo and you've gathered all these points that are in a city, and you get, your evaluation set is all these points in a city, and you classify all those points correctly. That's great, but if you're making a map for all of Togo is not a city, and so your model might do completely horrible in rural areas, but you won't know. So your evaluation data, testing and validation, they have to be distributed in some sort of random way. In this way that they're completely random, like a simple random sample over here, but you can also sample using stratifications. And you can see the training ones, the brown ones, they're actually a little bit more clustered. So I think we actually have some labeling efforts around this area, and so you can see there's a lot more brown points. But we'll move on. Those were the labels. Now we'll start taking a look at the Earth observation data. So we need some. We're going to import another couple packages, and we're going to get one particular label and take a look at the Earth observation data for that label. So this is what's in this label. There's the latitude, longitude, start date, and end date for which the label is relevant. There's a class probability, which is 1, meaning that it's crop. And then there's also a file name over here. Basically, this file name, we can run the next cell to look at it fully. This file name is a pickle file, and it contains the Earth observation data, which is essentially a NumPy array. There's some more information there, but essentially it's just a NumPy array. So in the next cell, we load this Earth observation data, and specifically, we're just going to print out the shape of it. This is pixel data, so there's no spatial dimension that's relevant. The 24 stands for 24 months. So we have 24 months available to us, and we can use either all of 24 months, or we can use subset. Like if for a particular country, the season goes from February to February, we can use those 12 months from this data. And then there's 18. And 18 represents the Earth observation bands, and they're actually displayed over here. So these are some of the things that Hannah was talking about in her first presentation. So in this Earth observation data, we have Sentinel-2, and so Sentinel-2 is optical imagery. So it's basically like photos, and in fact, these first three bands are actually representing the RGB bands. So if we plot these ones, in fact, we're actually going to plot these first three ones later, and you'll see the what looks like a normal satellite image. We also need other bands too, though, because 55% of the time the Earth is covered by clouds, and so if you're taking pictures of clouds with a regular camera, you don't see anything that's happening with the crops underneath. And so we have Sentinel-1 data from Sentinel-1. And Sentinel-1 is using radar, and so that can kind of see through clouds and give us that additional information. We also have precipitation and temperature information, elevation, topography, all these additional bands that give us more indication of whether something at a particular location is crop or not crop. And we have NDVI, which stands for Normalized Difference Vegetation Index. Complicated acronym. Basically, the way that I think about it, it's just like how leafy is something, how kind of green leafy vegetation is something. So if NDVI is very low, it might be a building. If NDVI is very high, it might be a forest, or it might be a field. So what we'll do next is we'll actually just plot the values from Earth observation bands for a particular time step. This is the 10th time step, it looks like. Just to kind of demonstrate that they have very different ranges. So this is another challenge that you have with Earth observation data is how do you normalize correctly? With RGB images, everything is from 0 to 255, for example, so you can kind of be consistent in the normalization. But here, as you add different data sources, you have to actively think about that. Okay, the next cell is a small challenge. If you run it, you're going to get an error. And there's a place where you have to put some code here. Basically, the goal is we're going to plot NDVI, like how leafy this particular example is. And so there's a non-crop label that we have to fill in, put some code in. So I'm just going to go through and kind of talk about how you might do that. We were looking at a crop label before. This time we're just going to be taking a non-crop label. So if I scroll up over here, I had a crop label, right? I printed it out. So basically, I got the crop label by querying the data frame and conditioning the query on it being a class probability of 1 and the subset being invalidation, and then I took the first example. So if I copy and paste this line and just change the class probability, that'll be a non-crop example. So I'm going to do that. I'm going to copy and paste this crop label, scroll down, and paste it over here. Change this to 0 and run this cell. And so I get something like this, and I get some links. We'll take a look at the links in a second. But this already makes sense to me because I was talking about NDVI being kind of the measure of how leafy something is. And we can see that it's very high in the month of August for this crop time series. And then it drops down quite a lot in September. So the reason that makes sense to me is because crops are harvested, and most likely this crop was harvested at the end of August. And so it was all leafy in August, and then it became a bare field in September. And we can actually take a look at these points by opening them up in Google Maps. So here's the crop one. I will open it up first, and I can see indeed it looks like a field right over here. And then if I guess I don't need this anymore. I'll close this. And I can take a look at the non-crop one. And I can see there's definitely fields around here, but if I zoom in, this one looks like it's in the Biancourt River. So this is non-crop. And you can actually, like, we're just querying inside of the data frame. So you can really change this number to anything. I think we have about 200 or 300 examples here. So you can change this number to something less than 200 and you'll get another example. And actually one of the fun ones I had was 75. So if I do 75 and then open up the non-crop one, I get something that's in a forest, but then sometimes you get like some interesting thing in Google Maps, like videos even. So we can quickly watch what the heck is going on here. If anybody can guess what this is, I don't have a prize, but I think it's a well. Yeah, probably a well. Yeah, so this is actually some of the, when you're working with Earth observation data, you can, look at things on Google Maps directly, and sometimes you get a better sense of what's actually happening. This point is not exactly where our point is, but it's in that vicinity, and so it's kind of interesting to even see like the sort of houses that are right over here. So that's neat. We'll close that. All right, I'll check if there's any questions in the Q&A. Looks like no, so everything is going smoothly. Okay, I want to just get a thumbs up if people got the NDVI plot going. Cool, easy. All right, so that's essentially the data. We looked at the label, we looked at the Earth observation data. Now we're actually going to train a model on this data. And so what we're going to do first is we're going to run this cell. And that's going to install a package called TSAI. Basically, it stands for Time Series AI, and it's a repository that has all sorts of PyTorch time series architectures made for you, so you don't have to write them yourself. If you want to write architectures yourself, by all means, but this is very convenient. Then you have to pick a model name. Maybe you can call it like your name, CVPR, or that's a boring name, but maybe you can come up with a cooler one, and maybe that'll be a factor in me choosing your model to make a map. So I'll call mine Ivan CVPR. Don't add any spaces or that kind of stuff. Let's just do, I think you can do underscores but no spaces. And then there's a train.py script. So I'm just going to start running it right away. And I only have it running for 3 epochs. But there's an optional challenge to basically actually look into the file and change it up, or even change the number of epochs. I'll tell you right now, if you increase the epochs even slightly, I think you'll beat out my model. And I'll show you the way that I would open up this file. Basically, if I go into the File tab over here and open up OpenMapFlow, that's the repository, and we're working the crop mask example. And so here's the train.py right over here. So you can double click on it and you can make it a little bit bigger. And I'll close this File tab now. And so this might look familiar to lots of people. Basically, we have some imports, and then we have a argument parser, and you can set things like the start month, for example, the batch size, the learning rate. We're using a default start month of February because that's the data for inference that we have is starting in February. Yeah, we even have the ability to use weights and biases for logging, and then all the code for the data loaders and the model over here. We can see we use this, and we're using a transform model that we imported from TSAI. And this is all the model code right over here. All we did was just basically make sure that our data is scaled down a little bit, transposed to be the correct shape, and then we fed it into this transformer model. And that's the model that we trained just right over here. So I have an F1 score of 0.65, which is F1 score is usually what we use for evaluating these models. And the reason is that countries do not have a balanced amount of crop or non-crop. And so using accuracy can be very misleading, especially if you're working in a desert country, like Namibia, for example, is mostly desert. And so your model can guess all non-crop and get 95% accuracy, but actually it sucks because maybe it can guess that there's no crop growing anywhere, but there might be. So I'm going to keep going, but there'll be some break time for you to maybe fiddle around and train a better model later. What we're going to do next is now that we have this transformer model that we trained, we're going to actually do inference over a small region, not over a large map, but just a small region directly inside Colab. I'll do a quick check over here. Oh, cool. Non-crop with sample number 20. Yeah, this looks pretty interesting. What folder is train.py in? Yep, I'll just write the answer right here. Train.py is an OpenMapFlow /crop mask example. There's 3 examples in the repository, and we're working with the crop mask example. Intro tutorial. Nice. Yeah, sure. Actually, I will show how to pull that up again. If you click on the file on the left-hand side on this file folder thing, you will see OpenMapFlow. It's a repository that we cloned. If you open that up, there's these examples: buildings example, crop mask example. This is the one we care about, crop mask example. If you don't open that up, there's a data folder, but we don't need to open up the data folder. Trend.py is right over here. So then you can double click to open it. Hopefully that's clear. All right, no more questions for now. So I will keep going. Okay, inference over small regions. So we have to import some more things here. And we have to make a couple directories. Basically, these directories are going to store some of the data that we're going to use for inference, and they're going to store our predictions. And we also make a small function here for merging our predictions together. Then we're going to download example inference data. So this data is in a public Google Cloud bucket. And so everyone should have access to that by default. And it's 50 megabytes. And I believe since this is on Colab, the internet speed won't matter because it's all on Google servers. Because if it's here, then it might take a couple seconds. But if you've got to this point of download, if it's all downloaded, then maybe give me a thumbs up just so I get a sense of if people got here. Okay, a couple people. So maybe I'll give it a couple seconds for people to get by. Maybe I'll take some water for now. If people have any questions too, you can just scream it out. What name goes in model name? It is your choice. What name goes in model name? Because that is the name of your model. So I'll answer it in Google Docs as well. But no spaces in the model name. I think that might cause issues. Yep, I will go back and show where I typed in the model name. If I scroll up to the train section, there is a cell over here which sets the model name as an environment variable. So if you run this, you'll get the ability to input your model if you click on the flashing cursor, and then if you click enter, you'll be able to save that model name. All right. All right, thumbs up if you have the inference data now downloaded from Google Cloud. Okay, nice, lots more thumbs up. Good to see. Okay, so we have the inference data. We're going to visualize it first before we feed it into our model. But before that, we have to actually merge it together because we downloaded a couple different tiles. So that's what this is doing. And it's merged our tiles, Earth observation tiles into one. And then we are going to run this next cell, and that's going to visualize the Earth observation data for 1 month. So this is what it looks like. You can see what looks like fields kind of in the middle and the left-hand side. Maybe there's a lake in the bottom left corner. There's a city or some buildings in the top left-hand side. There's maybe a forest in the top right-hand side. And if you remember, we talked about the Sentinel-2 bands, that Sentinel-2 has RGB. Here are those bands. We basically just took the RGB bands from the Earth observation data, and we combined them and plotted, and we got this. But you can plot the Earth observation data in all sorts of ways. You don't need to actually just be plotting RGB. Okay, yeah. Yeah, so the normalized part, this is a pretty simple normalization. There's different ways to do it. All we did here was we took we basically scaled it down by using the, okay, let me preface this by saying that Earth observation data, these bands are in the ranges of 10,000s. And so often the case is that most of the values are like 2,000 or 3,000, but then there's some that are really, really high. And so what we did here is we took the max from value from the data and the minimum value from the data, and then we actually times the max by 0.5. And then we scaled the values down such that the maximum number is 0.5 of the actual max. So essentially, if I would change this number to be the actual max, the resulting Earth observation image would just be very dark because there's some of these outliers that are like, yeah, you can see the top there. It looks like there's clouds, and they're making this whole normalization not work. But if I make the max much smaller, like even 0.4, it's going to make all these other pixels, it's going to clip basically the values. And so it makes everything a lot brighter. And now I can see what's going on. So yeah, so normalization is really up to you. And there, yeah, actually, like in the literature, people do all sorts of different normalization for our Earth observation data. What I have heard where people have had the most success is basically taking not the maximum, but like the 90th percentile maximum, and then using that to scale everything down to like between 0 and 1. We just use that normalization for visualizing. It's actually like in our model, we used a different sort of normalization, so it's not super relevant. Yeah. Yeah. This is just like kind of a toy example of visualizing, so we can use whatever normalization we want. Yeah, in the model right now, we have a very naive one, which is just divide all the values by 10,000. But in many cases, you would want to actually do like per band normalization, which would be like taking the maximum of each band. Yeah, in many cases the bands are similar in terms of like how big they are. But this is kind of just an example, so we made it as simple as possible, so that people are allowed to then play around with. Like basically, I wanted to keep that model code as short as possible, so it looks as less intimidating as possible. And then once people start to train the model and see, there's something interesting, these values are not being used, then they can dive into the normalization literature that is very fun to read. So I've left that out of this tutorial, but now people know. Any other questions? Okay, so this is our Earth observation data. Now we're going to make predictions with the model. So we load the model, and then we pass each tile into the model. And what's happening basically is we have this inference function, which splits each tile into the batch size that we have preset before. And then it makes these predictions, and it saves these predictions to these NC files. And the predictions are just values between, for every pixel, we have a value between 0 and 1, float values, with 1 being most likely crop, 0 being most likely non-crop. Once all these predictions are done, we need to merge them all together. That's what the next cell does. And then we can visualize them by importing a cool color map. And so this is the output that I get. And I can see at the top over here, it looks like it's kind of yellowish, so it means non-crop. And if I scroll back up, remember we had what looked like buildings over here. I clipped these values pretty hard, but you can see it looks like there's a whole bunch of little squares. And at the bottom, it looks like there's fields. And indeed, it looks like at the bottom, there's some green stuff. But this model is not super confident because I only trained it for 3 epochs and I didn't do any cool things in the train.py. So if you have a cooler output, something that looks more accurate, maybe you can post it in the Q&A. Oh, this is an interesting one. Oh, okay, I get you. Yeah, okay. So here's actually, maybe I'll zoom in to make this a little bit more obvious. So somebody over here, Catherine, basically took the non-RGB bands from the Earth observation data and visualized them, and you got a very different result. And so this might be a way to kind of analyze the data that you're dealing with. But if people actually, even if you have the same sort of looking crop mask example map preview, maybe you can do a quick screenshot and post it below. And I'll delete some of these things so that there's more space. Somebody did it for me. Okay. Maybe I'll leave this compliment to make myself feel better. Okay. I haven't seen any screenshots, so I don't know if people got there. Oh, okay. Oh, okay, cool. Yeah. So these ones actually, yeah. So some of these are definitely, there's more dark green over here. So the model is more confident about some of these crops. So that's kind of neat. All right, I'll be, two will be sufficient for now. All right, so now it's the deployment part. This is the part why we have to do all that work for cloning the repository and getting the token. First, we're going to run an evaluation script. And this is to generate the test metrics. And you might ask, didn't we already have metrics before when we trained the model? And you're right, we did, but those are validation metrics. It is very important, but not a lot of people do this, to have a validation set and a test set. Validation set is used when you're training the model to evaluate your different parameters, hyperparameters, maybe even different model architectures. But those numbers, you can't publish them and you can't show them to everybody because you have biased your hyperparameters on those numbers. So you have to generate separate metrics on a test set, and those are the numbers that you can then use to talk about how good your model is. So that's what we just generated over here. And they are lower. In many cases, they will be lower. But that's such is the life of making machine learning models actually work. And then we will use this DVC cell to push our models to Google Drive. We're not going to push the model file itself to GitHub because it might be a couple kilobytes or megabytes. Instead, we'll push to Google Drive and then push a reference to the model to GitHub. So it comes up with a yes/no question here. If I want to commit it, I do want to commit it. So I'm going to write Y and click enter. Sometimes you have to scroll to the side to see that because this is made for the command line. But once you click yes, then it's going to start pushing your model to Google Drive. And once that is done, then you can run the next cell, and that's going to make a new branch, add your files that you've changed. So for example, there's going to be a reference to the model. Commit those files to the branch, and then it's going to push them to GitHub. And you'll have this link, which says create a pull request. In my case, it says I've been CVPR, that's my demo. And you can open the link in a new tab, and that's going to allow you to create a pull request. And the pull request is going to go from, I'll make this a bit bigger too. It's going to go from your repository. So in this case, my forked repository is ivansolonkoff/OpenMapFlow. My branch is CVPR. And I'm going to make a pull request into the NASA Harvest OpenMapFlow. This should all be there by default. You don't need to change anything. You can add a description if you'd like. I am not. Just going to create a pull request. And there we go. So if you've got this far, I'm actually going to be able to see by opening up the pull request tab over here. And right now, it looks like, oh, Catherine was faster than I was. But we will see if this list gets populated as we go. I'll just quickly mention what's actually in this pull request. There's two things. One, metrics. Basically, we're going to keep track of the metrics in the repository. And the other thing is this DVC file. So this is a reference to the model that we push to GitHub, to Google Drive. And so this is a way that somebody else, for example, will be able to pull in our model from Google Drive. If they just do DVC pull data/models, they'll get the model that you have created. So let us check if there are other pull requests here. So it's only Catherine for now. One more thing that I will talk about is once I make the pull request, and another kind of advantage of OpenMapFlow is that we've been working with these kind of models for a long time. So we've ran into every possible bug possible, or we've run into a lot of bugs. And so we had to write a lot of unit tests. And so we've added a lot of these unit tests into the package as GitHub Actions. So inside the actual repository, we have some continuous integration tests, but then there's also data and model specific tests to just make sure that the models and the data is consistent. The data test may fail because from your repository, you need to basically provide access to Google Drive in your repository, but that's a fairly trivial thing to do. We just need to do it for this demo necessarily. All right, let's see if there's any new ones. Hey, all right. So now I can do some comparison and yeah, see which one I decide to merge, basically. So I'll close these other things. Maybe actually I'll quickly check if there's any questions. No questions. Okay, so I will open up the ones that are not mine and open up the files changed and look at the metrics. So we have F1 score of 0.66 for Catherine CVPR. We have 0.72 for this CVPR BGB. So this is a good candidate for being merged for now. And then we have Daniel, F1 score 0.66. So not beating the previous one. And then Ulysses, F1 score also 0.66. All right, so far I think this one is the king one. And I think I'll maybe do a quick additional check to see if there's any more pull requests. America's Next Top Model. I guess I have to check this one. And this is one of the ones where the name is so good that it would just have to be merged because of the name. Oh, and the F1 score is competitive. So we will close the ones that were not competitive. Sorry, Catherine. And sorry, Daniel and Ulysses Moya. And compare these ones. 0.72 F1 score and 0.71. Yeah, and that's the thing. The validation set is not, the validation set score might not exactly match the test set score. Okay, so I think I'm going to go ahead and merge this one. Actually, I'm not going to prove it. Since I have admin rights on this repository, I can just merge things even if there's red X's. But if you were trying to merge this, I don't think you'd be able to. So I'm going to confirm this merge. And so it's going to merge this particular model into the repository. And so if I go back to the repository homepage and go into the README, you can see there's all these different badges over here. So a lot of these badges are representing, actually all of them are representing GitHub actions. And one of the GitHub actions is called crop deploy. So crop deploy signifies deploying the crop mask model. And so you can see there's some checkmark ones, and there's also one that has a spinny thing, and it was started 21 seconds ago. So this is the model that we have just merged in. You can see actually there's a name right there. And if I open this up, let's see, there is things happening. But the main one that's going to happen is deploy Google Cloud architecture. So this might take a couple minutes. I think it's going to take about 5. So I'm going to go back to my slides to basically explain why this is even necessary. Like you might ask, like, why can't we just make a big map in Colab? And that's a very valid question. And so this is back on the slides just to illustrate what just happened. We just ran that notebook and we got an optimized model out of this. And what is actually happening now, before I go into why this is necessary, what is happening is that the optimized model is being packaged into a torch server. So that's a way to run PyTorch models fast. The torch server is being put into a Docker image, and then a Docker image is being deployed to Google Cloud Run, which is a way to run thousands of Docker containers. And this is all happening inside the GitHub action. And that takes about 5 minutes. And it's if your repository is public, then you have unlimited GitHub action minutes. If your repository is private, you have 3,000, which is still a lot. Yeah, if it's public, you have this kind of very nice resource available for running all sorts of tests, for deploying things. And so we use it quite a bit. And we provide all of those GitHub action scripts as part of the package. So we're going to talk about creating a large map, and then we're actually going to do it while things are being deployed. What we did in the training notebook is we did basic inference, basically. We took Earth observation data, put it into the model, and basically got one tile out, or one pixel for simplicity. And this is good for visualizing a simple thing. But if we want to make a map, that's going to be millions and millions of pixels. And so if we just did predictions for one tile or one pixel at a time, that would take a very, very long time, and it's too slow. So what we're doing now is we're doing predictions with thousands of models, or what we're going to do soon. And that is much faster. And we can do that because we have access to cloud computing now. And so that's fast inference. So I'm going to check on the Uh-oh, looks like there's an issue with this one. Oh, yeah, okay. So it looks like I won't be able to use this cool model because earlier today, one of basically the DVC Google Drive secret that's in the GitHub repository was expired, and I think it still hasn't been updated here. So I'm gonna have to use one of my own models, unfortunately. Sorry for the nice one, but this one will be kept in there, so you'll be a contributor to the repository. That's unfortunate, but it is what it is. Okay, so let's go to. So this is a README, and we have a section here which is creating a map. I'll click on that, and it's another Colab notebook. And so creating a map is only available through Google Colab, and the reason is that we're using Google Cloud and we're using Google Earth Engine, and it just makes things a lot easier to just connect those services right in Colab. So we use that for that purpose. All right, so creating a map, this is the notebook that I'm going to run on my own. So basically, there's no more interactive sections left, and I have to install OpenMapFlow. And basically, for this one, I don't need to clone any repositories because I'm just going to be accessing the Google Cloud architecture. What I do need is a configuration file to basically tell this notebook which models and which Google Cloud architecture to use. And so in OpenMapFlow, when you generate a project, you generate an OpenMapFlow YAML, which is a configuration file that has all of the information for that particular project. So if I go back to the repository and open crop mass example, there's an OpenMapFlow YAML in here. And I'm going to copy and paste this guy. And once OpenMapFlow is installed, I'll be able to paste it into here. And that way the notebook will know what Google Cloud resources to use. All right, so here it goes. I'm just going to write the file right over here. So basically what I just did is I just copied and pasted the OpenMapFlow YAML into this directory. And so now when I use OpenMapFlow, there's things imported like Google Cloud project ID and project, and these are just read right from the YAML file. It just makes things a lot easier in terms of working with the package. So we're going to import all those things, and then we're going to log into Google Cloud and log into Earth Engine. And so I will log into my account here and click allow. So I log into Google Cloud so I can access the models that are deployed, and I log into Earth Engine because in the event that there is no data available for the region I want to make a map for, I'm going to get that data from Earth Engine. But there's also the ability to use data that we've previously used, so you don't need to use Earth Engine necessarily. So this next cell, I'm going to, now that I've connected to Google Cloud, I can query Google Cloud and specifically use the Cloud Run service to check what models are already deployed. So if that GitHub action had succeeded and the DVC credentials are correct, then we would see that other model over here. But unfortunately, we have to use this toggle crop mask one. Then we will click available B boxes. This next cell, this is beginning the inference configuration. So basically, we're going to check what bounding boxes, what regions we already have data for. That's what this is loading, because we're not going to use Earth Engine. We're not going to get a whole bunch of new data. We already have data in our Google Cloud storage buckets, all these B boxes in general. And so we're going to use that instead. And we can visualize them by looking at this, using this widget. So I can zoom out and see what data we already have available. Here's all of Uganda. It's a pretty big one. We are not going to use all of Uganda because it is really big, big area. Instead, there's one at the bottom here. Yeah, this one's a little better. So it's only 1,000 kilometers squared, still pretty massive. but it's small enough that, that this won't take a long time. And we've previously made one with this one. So instead of check existing progress, I'm going to click create a new map. Oh, right. Well, actually, I should zoom in. Yeah, here it is. This is actually a pretty big area. It might not look like it because I was zoomed out to Uganda level, but this is much bigger than the one that we did as an example in the notebook. All right, so I have selected, I selected the model to use over here. The date's already set because the data is already available. The time and cost is not available. That's something that we'll put out soon because we're using Google Cloud resources to run this. First of all, the more data, the more time, and there's some costs associated. Everybody has, I think, $300 available on Google Cloud by default. And I think this would cost maybe $1 or so. This is like a pretty small area. And basically, most of the cost is in the storage of the data. And there's some cost of running Cloud Run, running like 1,000 models at the same time. But it's not really that large because everything is parallelized. All right, so we are going to take this configuration information, store it to some variables, and then we're going to start running inference. So I'm going to click over here, and gives me a status message, and it says obtaining input data 0, predictions made 0, and then it asks me if I want to move the TIFFs into the right spot to start inference. And so I'm going to press yes, and this is going to start moving all of the Earth observation data for that particular region into another folder, which is going to trigger the inference process. So I'll quickly just show what the heck is going on behind the scenes here on this next slide. This is what our cloud architecture looks like, and this is what you'll have the ability to deploy if you pip install the package and run the GitHub actions. The main thing, well, actually, there's a couple of things here. So what we just did is we were looking at our remote sensing data storage bucket. That's where we have all our Earth observation data. And we moved data from one location in that bucket to another location. And then that movement of the data triggered a cloud function. And the cloud function in turn triggered Cloud Run, which is where we have our model packaged in. And the model is packaged in that torch server, Docker container. And then it's multiplied up to 1,000 times based on the amount of data that we have available for inference. Once the model makes a prediction, in Cloud Run, we also save the predictions to a separate data storage bucket. And so we have all these different small tile or pixel predictions in another bucket, and then we'll have to merge them all together. So you can check on the progress of, I guess we can close these other guys. Stop model. All right, so last time that we ran this, we had input data available 196. So that's like 196 tiles available, predictions made 0. So if I run this again, it's going to show me a new status message, and fingers crossed, hopefully the, what's it called? The amount of predictions increases. So predictions made 196. So that's great. Inference is complete. Time to merge the predictions into a map. So we have all these separate pixels, and we're going to follow almost the identical process that we did in the tutorial notebook. And it's fine to do this process in Colab because now you're not dealing with Earth observation data. We're only dealing with the predictions, and the predictions are, for every pixel, it's just a value between 0 and 1. It's not like 12 months of data and every month has 18 bands. So this is a lot less. The predictions are a lot less data to deal with. They're only 50 megabytes. So we are running these next cells to basically merge these predictions into a map. There's a lot of warnings, but you can ignore those. I haven't figured out a way to suppress them yet. We'll pick a color map. This map will be under 5 gigabytes. It was 50 megabytes, so we can actually visualize it right in here. So we'll run this, take a look at the output. Here we are. And this is pretty cool, but we can't zoom in and we can't compare it to Earth observation data. So what we'll do now is we're going to upload this map to Earth Engine because on Earth Engine, we can actually zoom in, zoom out, and we can take a look at, compare it to some of the actual Earth observation data that's underneath and see if things are looking correct. So these next cells are going to do that for me. I'm going to type in my Earth Engine username. And now it says you can see the map upload over here. Maybe I will reload this. All right, so you can see that there's some spinny thing happening over here. Basically, this means that the map is being uploaded. We did a couple practice runs before, and they were 1 minute. This is a big map that was like a whole terabyte. Still only took 27 minutes, so not really a long time. We'll run this final cell over here to just get a small script or steps of what to do next. Once the Earth Engine upload is complete, click View Asset on the image just created here. So that's going to be this link. Click Import, paste the following script into Earth Engine to view the map. So we're going to copy and paste this. And we're going to go back over here. Maybe we'll do a reload and see if this guy's done. Nope. So this is a nice opportunity for me to drink some more water. I didn't front load the talk with water, so I have to now have the water. The thing too is Earth Engine. This is another thing where it's Google's computers in the background. So depending on the time, depending how much Google likes you, these times may change. Actually, it did happen before that. Like I was uploading some map in a demo, and it was literally double the time. But it was taking a lot more than 1 minute. So I expect this one to finish. But that's another interesting thing. Every time I do a demo, it doubles in the time at least. So I guess while that's happening, I'll just talk about some of the slides I have left, and then we'll do another quick check. So what we'll hopefully show you soon is a map, and we have made a lot of these maps, specifically crop or non-crop maps, using basically the initial version of OpenMapFlow. OpenMapFlow kind of stemmed from this crop mask mapping project, and so we've been making these maps for quite a while now for many different purposes. For example, change area estimation. So if you make two maps for different years, then you can use some specific methods to basically evaluate how cropland changed over those years. The Malawi map over here has been used for field data collection. So people were actually zooming in on portions there and going out to get more detailed data where there were crops. And then we hope to use these in the future for inputs to our yield estimation methods. Let's do another quick check and see if Google complied. Nice. So there's a check mark now. So that's nice. And the instructions were to click View Asset and then click Import. So I'll just wait for this to load maybe. And then paste the script that I had. So you can't really see the whole thing, but here it is. Click Run now and just talk about what's in the script. Very simple. I choose a color palette to make things look nice. I set center. I add 2 layers. I'm going to add the predictions on their own from 0 to 1 to have a cool map, and then I'll add a mask, which is just basically threshold at 0.5 because that's what will actually be used for a lot of downstream tasks. And I just have it just loaded right now. So I'm going to make this a little bit bigger. I'm going to click satellite mode, and I'm going to make it full screen. And I can zoom in over here. I'm going to turn off the mask and just have the map. So if I zoom in and I can then do things like this and kind of take a look what's underneath. And I can see there, it looks like there's some massive fields over here. And there's a whole bunch of small fields. And if I turn on this, this map, it looks like the model's very confident about these being crops. Some of these are crops. There's some yellow over here. And if I look back, it looks like these are some sort of shrubs or maybe trees. So this is not a fantastic model, but it does the job. And so, yeah, here's a mask as a demonstration also. And so you can make these for an entire country. It'll take a little bit longer, but not a crazy amount of time. Nice. Okay. So how you can get started is pretty simple. Basically, you install the package and then you run this command, OpenMapFlow generate, and it's going to generate a project for you that's basically what we just worked with. So it'll have that train.py file, it'll have evaluate.py, it'll have folders for data. The train.py file, it's pretty, you can basically, like there's a template, but you can do whatever you want in that file as long as you output a model that's a torch script model, basically. So yeah, this package gives you those three components: adding data, training a model, and creating a map, and then you can use it to make maps like the one we just made. All right, last thing I'll talk about is future work. Future work for this package is, one is to make data sets easily importable. Right now, we all have to clone the repository to access the data. In the future, what we're trying to do is basically just make it like Python imports, where you can import a data set that you'd like or that has labels that are relevant. We want to add multi-class classification to our to OpenMapFlow. Right now, it's binary classification only. Custom Earth observation data formats would be great, because then we can start including data sources like Planet Labs, which has a lot of different products coming out. And then training with the spatial dimension, so taking advantage of entire images beyond pixels. We haven't included that initially because we get a lot of information from the temporal dimension, but as we continue to do our work, we'd like to include the spatial dimension also. So that's OpenMapFlow, rapid map creation with machine learning and Earth observation data. I hope you kind of have a good idea of what it is. And it's a open source package. So if you don't like something about it, you can actually go in and change the code yourself. And if I think it's a good change, then I'll approve it, or Hannah or Catherine will approve it. So there's already issues written out there. So that's basically our entire tutorial. We talked about remote sensing data and its nuances. We gave an overview of Earth observation and for agriculture, that different applications. Then we demonstrated some use, or showed some use cases and example methods, and then talked about some of the ways that you can get labeled data. And then we just talked about OpenMapFlow and how you can actually get started with working on in this sort of area. So the key takeaway is that machine learning with remote sensing for agriculture and food security has high real-world impact and motivates foundational research. Thank you.